Yeah, thank you very much for having me. Very actually, incidentally, I gave my last keynote at ICASP. It's also in Singapore, so it's very interesting. Back to this beautiful city, and really enjoy. And today, I'm going to talk about the topic that very much has captured people's imagination in the past decade, right? The things about the intelligence. I mean, that's how this whole conference is all about. The title is about pursuing the nature of intelligence, right? It's a little bit big. I'll see if we can pull this off. So I think, we have seen a lot of talks, a lot of technology in the past decades, advancements. But it's very curious, right? There's many attempts about what is intelligence? Philosophical, mathematical, pseudoscientific, all the things. Psychological, everything's being talked about, right? And there's a lot of misleading bias, confusion, right, in the community. So the question is, can we make the study of intelligence scientific and mathematical and computational? Right? To that end, probably we start to ask some very annoying questions, but the basic ones. What is intelligence? What do we want to learn? How and why? Right? I mean, this is something. So I like the quote from Richard Feynman. Right? I cannot create it from first principle, I cannot understand. Okay, maybe just me, but I hope many of you resonate with me about that. There are two things in the world, right? Deserves, our ultimate attention. Is what is the origin of the universe, right? What's happening? It's physics, law of physics. The whole world is driven by the laws of physics. And then something magical happens. Life begins, right? How life evolves. Intelligence is very much the mechanism behind the evolution of life, right? Those are the two probably ultimate questions we are trying to understand as human being, right? I love this quote from Václav Havel, right? Just as the constant increase of entropy is the basic law of the universe, so it is the basic law of life, to be ever more highly structured and the struggle against entropy. This quote will go through the whole talk, right? So let's look at the starting of life, right? And from DNA to brain. DNA, in my view, is the first big model, right? It encodes the knowledge life has learned up that point about the external world, encoded. Right? And we inherit that from our parents, right? We copy it. And the mechanism for evolving, we randomly mutate and then selected by the nature. This is the nature's reinforcement learning. It does improve, but extremely costly, extremely unpredictable, right? Sounds very familiar with our big models these days. But it took about 3 billion years to another point, a magic moment where individuals start to develop brains, neural systems, and senses. The individual start to be able to acquire its own memory about the external world, the surroundings. See, barely after about 15 million years, very short time, that caused the explosion of lives, significantly improved the survivability, adaptability about life. Think about it. So hence, the biologists call this species intelligence called the phylogenetic, meaning that in this stage, early primitive life, individuals does not have intelligence. Species does, right? Interacting with the environment through reinforcement learning, it evolves. Now, after brain and the senses, individuals start to have intelligence, right? It's called ontogenetic intelligence. Now, it's very interesting. The higher form of intelligence has a very distinct feature. The higher form of life, right? You stay longer with your parents after birth. What does it mean? We rely less and less on our DNAs, our big pre-trained model. relies on our self-adaptability, self-learning capability. And here comes human. And human, something interesting happened, right? DNA brains. Humans start to develop language, written language. We start to share information. The efficiency of acquired knowledge significantly improves. And also, written language plays a role as our memory, individual memory. As the DNA, we can pass on knowledge, or actually it plays a role as a DNA, right? Now we can, for the first time, we can pass on our knowledge to the next generations. It records knowledge. So we call it societal intelligence. And about 3,000 years ago, something magical happened in our brain, right? Mathematicians, philosophers start to actually develop logic, mathematics. It's a new language, right? And also, that allows the birth of science, modern science, right? We are able to theorize with a hypothesis, then do experimental verification or do deduction to verify if our conclusions are consistent or with the assumption or consistent with the external world. This is, we call it science. So nevertheless, there are just different forms of intelligence. Distinct, nevertheless, right? So about the 1940s, a bunch of pioneers started thinking about how can we make machines to imitate intelligence, right? Started with a very, influential figure, Nobel winner. Right? He started the cybernetics movement. In fact, he actually affected the entire generation of scientists. Everybody here, right? Shannon. How we record information, store information. Right? Dong Newman. How we improve our decision making. Right? And there are all these scientists to study different characteristics, necessary characteristics or mechanism behind the intelligence of animal or human. Right? I call this is really truly magical era. This is the beginning of intelligence, machine intelligence. And at that level, they actually study one question, right? How do we perceive the world, learn knowledge, build our memory, and be able to predict the future? This actually, of course, led to Alan Turing's question towards the end of that era, 1950, right? Then can we distinguish human and machines? We'll talk about that later. So how do we start? I mean, intelligence is a phenomenon of nature. Hence, we learn from the nature, right? How our neuron works. We make mathematical models of neurons. Right? In fact, Warren and Waller was inspired by Wiener to study the behavior of brains. I think Waller was his postdoc at MIT for some period of time. And of course, after people learned, right, the model of neurons, they become very obnoxious. Right? 1950s, let's just now we understand how brain works. Let's just collect those neurons, build perceptrons, right? Spend millions of dollars, right? I mean, if you go to read the newspaper in 1950s, New York Times, everything we brag about today about AI has been bragged before, okay? Machines start to have intelligence. They develop consciousness. They can learn on their own. We're going to lose all our jobs, right? History repeats itself, okay? Or at least rhymes. Right? So, of course, everybody know what happened, right? It didn't work that well, right? And then people become a little bit humble. Maybe there's something we didn't know about our brain beyond the model of neurons. Right? 1980s, people start to, let's look at what else we can learn from the brain, right? Studied the brain of cats. Oh, those neurons are not arranged in a very random way, collected in a random way. They have patterns, organizations, maybe for a good reason. Comes to the convolutional neural networks, right? And then everybody knows a little bit of history. The slides I borrowed from Professor Rina Vidal, right? Captured the essence of natural, how the artificial neural networks, everybody sort of know this. But still, right, there's up and downs, but there are people persist, right? And The new thing started about a decade ago, 1912, very much powered by the availability of data and compute, right? GPUs and computers become very fast, data is available, and suddenly we are able to train neural networks, right? It's still very costly, but we can afford it now, right? And we can see the generations of neural network is proposed and iterated, become better and better, but we don't really quite understand. A lot of them are very empirical designed, trial and error, right? Does this sound familiar? Very familiar with the primitive form of life, early stage of life. Random permute, trial and error, may the fittest survive, right? From Alex, Google, I just mentioned a few, right? There's thousands of them didn't survive, okay? 一将功成万骨枯, right? We are like that. Yes, things progress, but very expensive, very unpredictable. That's it, right? Very simple. But it has a very big impact. Text, images, even scientific data. Yes, it works, but the methodology is very different. So the question is, do we want to stay in that 3 billion years of primitive life, or we want to move on? We want to understand what we have done, then find out what the future is, right? From now, our understanding about the life, intelligence, the early stage of life is just primitive intelligence. Barely scratch the surface. Individual doesn't have any intelligence. The species do. It's like ChatGPT. The model has no intelligence whatsoever. Combined with engineers from OpenAI, the whole system has a little bit of intelligence. Okay? So it's time we have to make study of intelligence a very principled, mathematical, theoretical discipline. Can we do that? Ask very annoying question, everybody. And that's what I started about 10 years ago. I started curious about, what is it doing, right? Then I go back to my very basic training as a young researcher, right? We ask very simple questions, right? Why do we learn? What's the purpose, right? Then how? Maybe the deep network is the means to the end. If we know the purpose, then the rest is just manifestation. Can we do that? So then we ask, why intelligence ever existed? Right? Why we want to have science? Why we want to have knowledge? Whatever. Because the world is not entirely random yet. Right? According to thermodynamics or the second law of thermodynamics, the entropy of the world increase. But we're not there yet. Right? We're not that yet. There's still a lot of things largely predictable. Life relies on that. Intelligent science learns what's predictable from the sense data of the world, right? And we build a model to predict. So, by analogy, in fact, everybody is Newton, including dogs and cats. He or she just doesn't know about it. Because they already built a very good model, predict, understand how gravity works, how trajectory of flying object works. They can predict it even more accurately than human. The only difference is that they encode that knowledge in a different code, not in the differential equations. They keep that to themselves. They don't share. Okay? But nevertheless, it's the same knowledge. Then this is about science. Then if this is a scientific question, then what is the common mathematical problem? Can we ever make this absolutely crystal clear? What the heck is the mathematical problem we're dealing with here? Right? Then it turns out all predictable information is coded as distribution that must have low dimensional support and in a high dimensional observed data space. Okay? Simple as straight line. Just the Newton's law. A particle with no force moves on a straight line. It does not show randomly anywhere in the 3D world, space-time. Okay? Make it predictable. You can write the equation for it. Okay? Restrict the constraint, the trajectory. Everybody talk about inductive bias. It drives me crazy, right? Everything that works, magically worked, inductive bias. It's a loaded term, right? So my view is that the only necessary inductive bias is that the distribution you're learning is low dimensional. That's it, nothing else. So why? Everything we do today has something to do with this, right? Why is it important? Low dimensionality allows us to predict things, to fill the gaps, right? Something's missing, we know how to fill. We see a partial observation, we complete it. Once we have the distribution, once we have the structure, we can do Bayesian inference, even when we see part of the data. Generate the image, complete the image, predicting the next world. It's like doing the same thing, nothing else. Very simple. And also allow us to infer the truth despite the observation can be noisy, right? Empirical Bayesian. If I know the desired law is low dimensional, I can push the noisy data to that ever lower dimensional subspace, lower dimensional trajectory, lower dimensional distribution. Denoising. People have been doing this forever. Now, the modern generation model based on denoising. And we'll talk about more about it. And also we see corruptions, right? Data do not follow the law. What do? We correct it. We know it's wrong. Right? We do that. We harness the low dimensionality of the data. We can do magical things far beyond the human capabilities. Can recognize images far beyond the human capability. Right? If you can harness those structures properly, correctly. Okay? All this thing has something to do with the distribution we're trying to the data is actually highly low dimensional. Now, hence, to me, probably to all, right? The main objective of learning is identify distribution with extremely low dimensional structures from sense data and transform them to a compact structure representation. We call it a memory because we're going to use it for the future. We organize it. How do we formalize this mathematically? For any distribution with low dimensional structure, then there's a measure. How do we measure the information content in the distribution? We call it entropy. It goes back to Shannon, right? Or volume, right? For someone not familiar with information theory, it's just volume. There are very few basic quantities in the world, right? Energy, space, time. Entropy has something to do with space. Okay? Well, if you have a discrete random variables, that's the discrete entropy. Or if you have a continuous variable, it's called differential entropy. There are some caveats. We'll talk about that later, right? Now, then how do we learn? How do we learn that if we know our target is low dimensional, right? The universal mechanism to learn something low dimensional, start with PCA, ICA, sparse representation. You compress, right? You denoise to reduce the entropy of observed data distribution, right? For example, our observation can be, imagine you're a creature living in a one-dimensional world, okay? And you are the Newton of that world, right? But your observation is a little bit noisy, right? There's an empirical distribution, and you see some, observed. Red dots, blue dots, right? There's some noise. Then what do? Well, let's push them to where it's more likely, right? The probability is higher. Let's push those towards. Do that a few times. Somehow you see all the masses of the sample start to concentrate on some spikes. Zero-dimensional spikes. Voila! You can write the equation, right? One equation, reduce dimension by 1. You get a 0 dimension. That's the law. That's Newton's law. That's why in the whole world, right, all the physics laws are written, expressed in terms of equation, except one. Thermodynamics, right? The entropy is the inequality. always increase. But all the other laws are equalities. One equation reduces dimension by 1, another one reduces dimension by 1. They are all restricting the possibilities, reduce dimension. Let's generalize a little bit, right? Of course, we're not living in a one-dimensional world. Higher dimension, nothing's different, right? We add noise to our observation. Of course, if we start to, everything gets diffused, the entropy increase, all right? But we don't like it, right? This thing that we don't like. Remember, intelligence is a fight against entropy, against the diffusion. We're interested in the diffusion, the inverse problem. We denoise. Right? The inverse process is the most important one for intelligence, for discovering the structure, right? They actually can mathematically prove if you do the denoising, conducting empirical Bayesian, the entropy of the resulting distribution decrease. Okay? And hence you can do this iteratively. Decrease a little bit, little bit, little bit. Eventually you converge to the ground truth, the true low-dimensional distribution. Hence conceptually, this is exactly this picture, except dimension is a little bit larger. Okay? You converge to, and that's the magical sauce behind, the simple idea is behind the most powerful generative model these days. How we generate images, text, so on. Very simple. Conceptually, it's exactly the same as PCA, ICA, sparse recovery, nothing else. Okay? Well, there's something left unsaid, right? Yes, this taking the gradient of the density, right, pushing the data into a higher density area. I don't know the distribution, right? I don't know PX, PZ. How in the world, what is this operator, right? I only have some samples. How am I going to implement this, right? Mathematically, what that is? It's not a PCA. I can write a formula, right? Well, let's try, right? Well, if we're bold enough, we believe network can do anything, let's just try with some transformers, ResNet, right? To approximate this operator. Yes, it works pretty well, right? But it's empirical, we don't know why, we don't know how to improve. Well, let's go back to the basics then. If we know the distribution has certain forms, we have been doing that for hundreds of years. If the data is, let's say, one subspace, one Gaussian, or maybe a mixture of Gaussian, mixture of subspaces. If you're good at mathematics, you can actually derive what the operator looks like. Exactly looks like. Looks like what? Softmax plus a projection. All right? What this looks like? Looks like a little bit of prototype of transformer does, right? If you recognize the operator a little bit. That's exactly what it is. Hence, then we get both, right? If I have a very more general distribution, why I can just approximate with piecewise Gaussian, piecewise linear? It's a universal approximator for distribution anyway. Almost, right? If the distribution is benign, this is what I can do. But there's some caveats. This caveat actually troubles me for about nearly 20 years. About 20 years ago, I was working with René Vidal. We're trying to understand how to estimate low-dimensional subspace, mixture of low-dimensional subspaces, mixture of Gaussian, but they're degenerate. But if you go to, classical statistics and inferences, or even information theory, if you're dealing with low-dimensional structures, the differential entropy is negative infinity. It's not well defined. Or the maximum likelihood blows up to infinity. Then how the heck do we compute? How do we compare? If all the entropy is negative infinity, how I compare some low dimensional against some other low dimensional? Which one is lower dimension? It's a technicality, but it troubles me a lot, right? Then I actually found the answer in the thoughts behind Shannon, why he decided to start the coding theory. Because the differential entropy is not computable. You have to approximate it. If you want to have an encoding, decoding scheme that is actually implementable on a finite resource machine, you have to quantize it. And well, today it's a very sexy name called tokenization, right? So what do? You pack the space with epsilon balls. Measure the volume, right? Label the balls. That gives you explicit code book. Then any event happening in the space, you can see which ball it falls into. That's the code. You also can decode it, but up to just the epsilon precision. You can control that. Hence, the number of balls, number of bits to record the ball, it's called the coding length, coding rate. And also, for any distribution, the number of balls you need to cover the support to code it up to certain precision is called the rate distortion. You can calculate very precisely. Right? Hence, now we have an explicit way to construct codebook. Code our real data. Now, the next thing is, how do we measure the gain of it? Right? If I know anything could happen in space, I have no knowledge of the world. Anything could happen. It's a blue sky space. Hence, I have to pack the entire space with epsilon ball. Every ball is possible. But after a while, if we observe the world, well, only events around those blue ones occur. There's only 2 seasons, summer and winter. We don't need the rest of the blue balls, right? We gain some knowledge about the world. If we know the location of those green balls, we reduce number of spheres, balls, to a smaller number. Hence, the gain of information is precisely reduction of the coding length. This is a measure of information gain, right? The whole against the parts, right? The ignorance against information. The difference is your gain of knowledge, gain of information. You can actually measure this quantitatively. No longer just talk about it in abstraction, okay? Hence, the difference between ignorance and what's really the distribution of the data is what we call the information gain and also the rate reduction. You can measure it. And hence, you can actually put it. Now, of course, remember, we approximate distribution with a mixture of Gaussian. Then we can write down this in explicit form. A mixture of Gaussian, you can actually write it down. It's just everything said today. The mathematics is college calculus, nothing else. Okay? You can understand everything by just knowing linear algebra and calculus, right? Then you know this is formula. We call it the difference. The whole minus the parts. Now, how do we, this looks a little bit complicated, right? Remember, we try to compress, we try to reduce the coding length. How are we going to do it? This looks very slightly log determinant, multivariable, right? I mean, we have to go check your calculus, know how to do. Then, well, of course, we want to know the global optimal, right? What is the global optimal to achieve maximum compression? What do? We don't know, right? Nature is not that smart, but they can do incrementally. Let's take the gradient of this function. Since this is something we want to optimize, I can calculate the gradient. Go descend. Descend around it. Then as soon as I realize that, just calculate the gradient. Then you realize the operator of the gradient looks something magical. Looks like a residual network, with next, or looks like a mixture of expert. It has this multi-structure. It's exactly the same. And also, this function looks a little bit complicated, right, to average people. But turns out this has a beautiful landscape. Amazing, right? The maximum optima of this object function all corresponds to subspace are orthogonal. Turns out, even the local, all the critical points has binary properties. All the saddle points are writable ones, are regular saddle points. Basically, greedy descent will never stuck on those local minimas, critical points. And even the local minima, if you manage to converge onto it, it also corresponds to a configuration of your data associated with orthogonal subspaces. They organize, once you reach those critical points, basically, the solution is well organized. Can we do better, right? Not only we want our distribution to be orthogonal subspaces, we want them to be sparse, aligned with axis. So if we add a regulator, remember, right? Not only make them orthogonal subspace, we also align the subspace along our axis so that the representation is the sparsest. So we call it a sparse rate reduction. Right? We identify the distribution. Now repeat with me, right? We start with the blue sky. We compress to find where the green balls are. Then we start to transform them to make them orthogonal, linearize them, and also make them align with the axis. That's it. That's representation learning. So our conference is called the International Conference on Learning Representations. Define representations. This is it. This is how do you define what the representation you're looking for mathematically. So again, same exercise. This is something we want to optimize. Then apply a descent algorithm to optimize it. Computing the gradient descent. Everybody can do it here, right? With college mathematics, this is explicit formula, multivariable function, calculate the gradient, sort out what the gradient looks like, okay? So this object function has two terms, right? Three terms. One is about compression. Remember, we want to find that Green's area. The other one is about the max, make them orthogonal, right? Compress, cluster, what's similar? Contrast, what is dissimilar. Very simple, very basic, right? That's all. This is all there is. Then computing the gradient. Very incremental operator. Allows you to compress and contrast. Then what they look like. Look at those forms. They look like this. We're engineers, right? Once we compute, we don't like a mathematical formula, but we like diagrams, right? We can also draw diagrams. Oh, they look like, what they look like. They look like transformers. By the way, this is the most basic way of deriving this gradient, right? There's 300 years of doing gradient descent. There's many, many different forms. We just scratch the surface. This is just barely exercise, okay? There's much more advanced way of doing gradient descent, and we haven't get started yet. Then you stack, you repeat that process. You take one gradient, another gradient, right? You repeat, stack those operators one after another. You do this iteratively. What do you end up with? You end up with a network. It's just terminology. And this network is fully interpretable. Not only every layer is a gradient of a clear object function. And overall, remember, it's doing compression, right? So the parameter of the network are precisely the code book you are learning. Remember the center of those blue balls, right? You are learning a code book, explicit code book to code your distribution. And you use that code book to denoise, to compress, to transform, okay? But you don't know the code book. We don't know. DNA uses a different code book. Our brain neuron uses a different code book. Language uses a different code book. Chinese, English, British people use different code book. Okay? Science uses a different language. Hence, you have to learn that code book based on the data, based on any supervision task. Hence, backpropagation is precisely allows you to update your code book. The whole network is an encoding, decoding scheme. That's it, else. And you can hence start with empirical transform, you end up with something fully explainable, right? Neural networks. We call it crate. Rate has something to do with the coding rate, right? It's just doing coding, decoding, nothing else. And not only it's fully mathematically explainable, every layer, the whole network, every parameter is fully mathematically, statistically, geometrically explainable. Also, turns out something interesting. If you train such a network with any supervision task, the heads, the subspace you learn, you can visualize it. They start to have some semantic meaning, right? Each head tends to, maybe the body of the animal, legs of the animal, faces of the animal. We never label them, right? They just gather statistically, geometrically, similar. Remember, cluster similar things, separate different things. That's exactly what a network will do once it's optimized. This is just the beginning, okay? We barely scratch the surface. As I said, we just take this stupid, well, not stupid, but it's actually, very universal object function. You take the gradient. They're very simple, right? Look at what the gradient look like, and use that to construct a network. But remember, there's how many variants of gradient descent we have today now? We haven't started. Conjugate gradient, preconditioning, acceleration. Nothing has started yet, okay? You can do that within just last year. My group already has several iterations. Now we design new networks. We no longer we don't need 10,000 GPUs to try. We don't need 10,000 engineers, 100,000 engineers to try. Right? Different groups try different architecture, claim, well, this works better. No, we don't. We have a clear direction. This is what we optimize. The current gradient descent is not good enough. We can make it faster, right? The same network is scalable. And also, the attention part is quadratic. Turns out it's not necessary. Let's take a variational form. This is actually a paper we published in this ICLR. Just to remember the object function we try to optimize. Take a variational form. This gazillions of tricks, right? If it's non-convex, let's convexify it. Let's introduce different variational form. I think Renee is expert in that, right? Everybody can do it. I can make the optimization much more efficient. Guys, right? And also, there's MLP, it's very generic, looks ugly, very expensive. Is this necessary? What it does? Can we get rid of it? Yes, of course you can. You can actually mathematically can prove the MLP is not needed. You can still do denoising with operator at attention layer. And the convergence rate is linear convergence. You don't suffer. At least qualitatively, you don't suffer any convergence rate. You can use optimization, principal optimization, tricks of optimization to design God knows how many generations in the future. Make it much more efficient, much more compact. 300 years of optimization. Ideas all going here. We have not started yet. Okay. So this is just give us a little bit of idea, right? If you know what the learning is trying to do, know the objective. The deep networks is a means to the end. It's not an object of itself. We don't study networks. We study what it's trying to help us to achieve. But is compression enough? I started with some data. I tried to compress it to learn what's internal structures. But that object function is very weird, right? It's some non-convex. What if I get stuck with local minima? Or what if my data is not enough to cover the entire distribution? How do I know my memory is complete? How do I know my organization is optimal? Nobody knows. And what do? You use it. You use your memory to predict. Your limited memory, your current memory to predict the future, right? To regenerate. See, our brain, we generate not for the sake of generation. We simulate the world because we want to predict. Okay? So we want to see if my prediction of the world is the same as my observations. If my memory serves me right? If there's a difference, I try my best to decode, to auto-encoding. Turns out, actually, this is a problem Hinton has been working on for about 2 decades. That's very much inspired him with all his work on auto-encoding, nonlinear PCA, right? Even the work with Helmholtz machine, Boltzmann machine, backpropagation. All his work in the 1980s is very much focused on getting this problem somehow addressed. Okay? But now, of course, in the past, people do auto-encoding with all the networks, empirical design, right? But now this is an exercise we published. Some of my students did the exercise, right? Now we know compression, denoising. We don't have to guess the network anymore, right? For us, it's exercise. Because the denoising operator, diffusion operator, all we have to do is change the sign, the white box, where we remove noise or add noise. That's it. It's fully interpretable, right? The mutually inverse process. And it's a white box. Then can do exactly the same compared to He Kaiming had this Max auto-encoding paper, right? The encoding, decoding, he guessed it, right? He tried, God knows how many versions he tried. We don't try. We don't test. We just derive. Right? This is what they should do. See, again, right? This problem, we try to decode, have a memory, precisely decode the world, right? X and X hat has to match. We didn't, not me, not Hinton. In fact, this is the problem inspired the Nobel winner, 1940s. How animal form its memory. Okay? Be able to predict, right? X and X hat has to be coincide, has to be the two distribution has to be the same, right? But obviously, they're not start with the same, right? There's a difference. Then what do we do? We try to improve our memory, make our distribution better, right? For the next time, my prediction distribution will be better. Hence, I can use the error, right? My prediction with the error to change, come up with ways to change my memory, right? Unfortunately, or fortunately, nature does not have this option, right? In order to do this, you have to compare distribution in the real world, the real data. Do we ever do that? Does animal have that option? Everybody knows the screen is rectangular, right? Are you sure? How can you be so sure? Have you ever measured the angle? Do you carry a compass? Do you carry a ruler in your pocket when you grow up to measure a circle is a circle? Does the animal have that option? It doesn't. It learns inside the brain. It never accesses the real world. It does not have access to the distribution of the data in the world. We do. When we train neural networks, OpenAI engineers, we have that. We control both ends, right? If X doesn't look like, we penalize X. If Z doesn't look like very well, we regularize X. Animal, we don't have that option. Nobel winner knows that 80 years ago. We never learn open loop. We learn closed loop. We check using the error. We predict it and perceive it back in our brain. See if my predicted perception is the same with what I'm currently perceiving. It's called a predictive coding in our brain. We use internal errors to make our representation of the world self-consistent, not consistent. Consistent is exterior, right? This is intrinsic, consistent. Yes, you can do that too. Turns out, precisely, this is doable. This is doable under the assumption the distribution is X you're trying to learn outside is low dimensional. The dimension is sufficiently low. And then you can do this intrinsically. Mathematically, you can actually prove that. This is a paper we had done. And experimentally, you can actually do this. Right? This is some of our early attempt. Also, some has something collaborated with Yana Kuhn. Right? If you formulate this, learn this in a closed form fashion, use a minimax game. Similar to game, but not quite. Right? And this is doing this internally with a closed loop minimax game. You can learn. And magical things, we know open loop system, right? If you retrain it, catastrophic forgetting. Now everybody fine-tune big model, they don't talk about the catastrophic forgetting anymore. It's still there, okay? Trust me, it's still there, okay? And just because you ignore it doesn't mean that it doesn't exist, okay? Turns out closed loop system, they forget very gracefully, right? Just like our memory. And very interestingly, we get some confirmation from the nature, right? All the characters, sparse coding, subspace embedding, predictive coding, they are everywhere. They are ubiquitous, okay? In nature. All intelligent systems learn in closed loop, not end-to-end, for God's sake, okay? There's no open loop system alive in the world, okay? The why everybody's saying end-to-end is a good idea. I'm very baffled, okay? Very, very confused. So this is a paper actually about during the pandemic. I have nothing else to do. So I was at home and I said, let's just write something with, this is Doris Chow is a neuroscientist at Berkeley. He studied memory in monkey brain. He is a crazy doctor about doing all this. But we actually talk about how the memory works. So we wrote this paper and said maybe, what is the memory part of intelligence is actually maybe just pursuing parsimony representation and learn that in a self-consistent way. That's it. And I think, incidentally, around 2020, right, Hinton gave a talk at Europe's keynote. He started looking at maybe, the nature doesn't do backpropagation. They cannot afford it. Then what the heck is going on? Maybe they're doing forward optimization or both ways, right? We have to explore new things, right? And also the whole loop. The whole world, his paper for the optimization, right? The first page, he admitted nature correct error, never learn using backpropagation. You learn with closed loop feedback, okay? Now, talking about the principles, mathematical theory is not enough, okay? Everybody say, we want to compress. But how? Actually, it took computer scientists about 80 years, even more, to figure out how to implement. Right? Some people say, big model is minimizing Kolmogorov complexity. Absolutely wrong, okay? Kolmogorov complexity is not computable. That's the very contribution of Turing. Tell us what's computable, okay? But can you afford computable things? Absolutely not. They're NP-hard problems, right? We can only probably try with polynomial complexity algorithms, right? Can you also afford polynomial algorithms? No, nobody uses Newton algorithm anymore. Why? Everybody uses BP, everybody uses DNN. Why? Because they are probably linear or quadratic complexity. They are scalable. That's why they're popular. That's why we can afford it, right? Is scalable good enough? No. We need megawatts of GPUs clusters, right? Our brain is only 10 watts. Small, rat is only probably 1 watt, right? We have about at least 10 magnitudes away from the nature, efficiency of nature. Nature does not do backpropagation. Nature does not do global optimization. Nature does not have the option of 10,000 GPUs, okay? Our brain, our cortical columns, our cortex looks very different, right? It's massively parallel, distributed, hierarchical, auto-encoding systems. Probably, remember the history, right? Whenever we struggle, once we don't hit the wall, we never become humble in front of nature. Maybe it's time. I guess we're getting diminishing return right now with what we're doing, right? Maybe we should get a bit humble, right? Intelligence is not a game for billionaires. Intelligent nature has democratized, has open source intelligence billions of years ago, right? Should be affordable. Maybe it's time to learn. So far for the past 10 years, everybody trying to convince you, let's build a big enough model, end-to-end network, train it. It does not learn itself. We need 1.0, 2.0 iteration. Right? We have to close the loop. Allow the network to evolve on its own, to build a brain, to have nerve system, have senses interacting to learn on its own. One loop is enough? Absolutely not, right? We have 5 senses, different areas of brains processing different senses, then aggregate, congregate. Very highly parallel, highly distributed, highly efficient, right? And from continuous signals to discrete languages, right? So these days, a lot of people say we're dealing with multi-model large models, right? The language and the visual or other modality together. Again, language is not a modality. Language is a code book. We learn to store the information we extracted from those modalities, okay? Let's make that absolutely clear, okay? Anything says language is a modality is completely wrong. It's a code book. So we try to learn. We code information, just a very tiny bit of information, that we learn about the world that is shareable, deserve to share, deserve to pass on to our kids, besides our genes, our DNA. That's it. Okay? Hence, what is intelligence? After all this, I hope I have built up you to something very simple. Right? Intelligent system is the one that has a mechanism to self-correcting, self-improving its existing knowledge. Right? Well, let's do some pseudo math, meta math, right? Knowledge is the integral of intelligence. Intelligence is the derivatives of the knowledge. So everybody talk about general AI, right? The thing, if I memorize enough knowledge, the system is generalizable. Absolutely wrong notion. Intelligence is generalizable. The ability to acquire new knowledge is generalizable. You can remember all the knowledge we developed on Earth up to this point. Once we drop you on Mars, what do you do? Different planet. What do you do? We still adapt. We have intelligence is generalizable. Okay? But no system, not GPT-4, right? You should ask the question, anything without such a mechanism, however big, does not have any intelligence. Compared to a new baby, compare GPT. The DNA does not have intelligence, but has knowledge. Right? New baby has intelligence, only have knowledge in its DNA. But this baby can become next Einstein, can add a delta to human knowledge that the GPT-4 would never, ever dream to do. Okay? Very big difference. So now let's look at the history, right? Intelligence, there's some very common behind intelligence. But the mechanism can be a little bit different, right? So what's common? Every intelligence trying to learn a code book. Then you try to encode certain knowledge that code book is best for. But the mechanism, the optimization mechanism to improve the code book, to improve the information stored by the code book, can be a little different. Early stage of life, reinforced learning. Later, feedback control, feedback loop, right? Our early before science, empirical knowledge, trial and error, right? Generations of trial and error. But with science, something changed. The code book became precise. Even the practice, the mechanism changed. See, we no longer learn passively. Be able to serialize, be able to hypothesize, then do deduction to verify mathematically or verify experimentally if the assumption hypothesis is right. That's active learning. It's exploration, right? This is a mechanism never before we had this, right? We call it artificial intelligence. So if you put an adjective in front of a long, you better be very clear what you try to describe, okay? What do you try to define? This is a proposal, 1956 proposal, okay? So attempt will be made to find how to make machines use language from abstractions and concepts, solve kinds of problems now reserved for humans. Not every human, actually this means scientists, and improve themselves. Let's do a comparison. Today's AI we have been doing. I'm not talking about the hypes. I'm talking about the mechanism behind today's AI, right? Deep networks, transformers, and so on, what they're doing. We're doing denoising, compression, object recognition, image generation, text generation, reinforced learning, right? Look at 1940s, right? Signal processing, image processing, prediction, error correction, optimal control, game theory. Now, look at the 1950s. What is the proposal in artificial intelligence? Abstraction, logic deduction, causality, hypothesis testing, forming testing, problem solving. We're not doing any of those. Transformer is not doing any of those. Which one is more similar? We're doing animal intelligence. In fact, we're not even building a complete system at the level of animal intelligence. We're building a fragment of memory, however large that is. Okay? Let's just be honest. We're a scientist, right? Be strict, be rigorous, be clear. Okay? No loaded words. Right? The reason we develop mathematics is because we don't do research using natural languages anymore because it's ambiguous. Okay? We should know better. Now, this is a time for heroes. Right? 1940s is an era of heroes. People started looking at the mechanism of intelligence. Control theory, system theory, information theory, game theory, computing machines. Right? Towards the end of the era, 1950, Turing asked the question, right? Can we separate machine and human? But there's a flaw in his test. Right? But at that time, maybe it's enough. The flaw is not very clear. It's a guideline. This test is not implementable. It's not scientific. Why? The C part. Right? Who is the judge? A human cannot tell. Which human? What question he should ask so that the conclusion will be scientific or statistic? Right? No, there's no answer for that. It's a guideline at best. So maybe it's too early. But to this day, especially some people claim they're machines with super intelligence. We have to be more serious. What is the test? Should it consist of? Some benchmark? How do we separate a few things? Test the system. They just memorize facts, memorize something. Or they really understand something. How do I differentiate, right? A machine just memorizing enough numbers versus understanding the notion of natural numbers to the infinity. Right? Or is the system can self-learn? Right? That's the question Wiener asked about 80 years ago. I call it the Wiener's test. Can a system, machine can generalize hypotheses, assumptions, mathematical assumptions, theorize something, hypothesize something, either check mathematically the assumptions are self-consistent or the theory is consistent with the real-world observation. That's the modern science, modern mathematics. Right? Can do that. This, I call it Popper test, Karl-Popper. Right? All theory are falsifiable. All theory needs to be verified experimentally. Right? So on. That's a completely different process of improving our knowledge. That's a different behavior of intelligence. Okay? We're not there yet. Okay? This is a question we should ask. This is a question academia should work on. Okay? We barely scratched the surface of intelligence up to this point. In fact, we forgot a lot of valuable lessons pioneers of intelligence have learned 80 years ago. May that be a very bitter lesson. This is the bitterest lesson. I think in history we'll be judged on that. So today I just gave you a lecture, right? It's the past 8 years. My team has been taking effort to understand, can we make understanding intelligence as different forms of intelligence, different levels of intelligence as a scientific, mathematical, computational problem. Make it precise, make it rigorous, make it from first principle. Okay? What do we have learned? All intelligence is going after something parsimonious, low-dimensional. Those are in terms of laws, our memory, our languages. Right? The universal mechanism to approach, to learn, compression, to maximize information gain, to learn more about the world, the data distribution. How do we know the compression result is correct? Use it, decode it, use it to predict. Say if your decoded estimation is consistent with the observation. You can do that in either externally or internally to ensure that the memory is self-consistent, increasingly self-consistent, self-complete. That's it, right? So I love Einstein's quote, right? Because this quote says exactly the two principles. He's talking about science, making everything as simple as possible, but not any simpler. The first sentence is precisely about science pursuing parsimonious explanation. The second is precisely say that this theory needs to be consistent, self-consistent. Okay? Not any simpler. Right? So in Chinese, I summarize, right? In the past 10 years, the technology advances, very many manifestations. 对吧？中国人讲术，对吧？千变万化。道 right? Method, right? 思想、道理、原理，大道至简 as simple as possible, right? I believe nature, right? Intelligence follows very basic unifying laws, right? But the manifestation can be very, very diverse, very, 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 confusing sometimes, just like the physical world. Intelligence. So today, just give you a little bit of framework. Of course, all this mathematical, algorithmical, computational, and experimental evidences we collected in this new manuscript. Right? We call it How to Learn Representations of Data Distributions. And with some of my colleagues and my students and also postdocs and different locations. And see, these days, many young folks come to me, say, we don't compete with the industry, I don't have the resource, I don't have the data, I don't have 10,000 GPUs. What I'm going to do is the AI, right? Intelligence, right? This is one way, right? No. It's a golden time for academia because we barely open the door. We understand tiny little bit about intelligence, all right? And in the past 8 years, it's just multiple universities, right? And multidisciplinary from, TDI, Johns Hopkins, Columbia, New York, and Illinois. We don't have resources. That's why we're a big team. We do all the experiment, we distribute all the experiment. Some people run this, some people run that. That's it. We just have dozens of GPUs. But the ideas are fascinating, okay? We're progressing at a light speed. Because once with principle, right? We don't need that expensive process to progress, all right? So that's all I have to say today. Thank you very much.
Thank you very much. We have time for a couple questions. There's microphones there and one over there.
Hello, Professor Ma. Very impressive talk. Thanks a lot. So there's a thought I have pondered for quite a while. I want to hear your opinion on it. So if we look at early forms of life, intelligence kinds of emerge from the basic instincts where animals try to get to food and stay away from danger. Do you think that's like a prerequisite for enabling successful self-learning, also the loop-lean learning, and all the emergence of the more complex intelligence? Or you think the instinct part can be skipped in order for us to do the rest of the stuff?
That's great. That's a very, very good question. So, in fact, I think early form of life with DNA primitive animals just try to learn what's predictable in the very surroundings. Actually, there's a very interesting fact. You know that some very primitive, even single cell animals, their DNA is longer than human, has more strand, right? So basically, they have the mechanism to accumulate knowledge, but not all that knowledge are useful, right? Later on in the evolution, maybe some pieces, some part of the environment that memorized has nothing to do as they survive. So they get disappear, right? Because they consume energy, right? So hence, later on, there is a selection process, right? Certain reward associated with survival comes in. Because nature is trying to be parsimonious, not in terms of seeking knowledge, but also in terms of consuming energy, resources, right? So hence, those reward will help the animals to select which piece of information should memorize more. Remember, not only identify those distributions, also we organize them in our brain, right? The second part is just organize, keep. So I didn't get a chance to talk about those, right? So basically, we put probably higher weights on knowledge that serve us better. right? So that's an additional process, right? Has something to do. But nevertheless, it's all about learning the importance of samples of distributions and memorizing our brain. Right? Thanks.
A very quick follow-up. So if there isn't this intrinsic reward, and if we still try to do this self-learning process, do you think in the long run it will become very chaotic or unstable?
No, I don't think so. I think nature is very, very simplifying. I mean, nature does things. See, everybody talk about scaling law, right? Say, sometimes I made some remarks on social media that E doesn't believe in scaling law. No, I believe scaling law. I study statistics, high-dimensional statistics. We know, right? We think scales up. I mean, data sample size scale up. I mean, that's the magic thing happens. But we should be careful what we're scaling. Nature scaling what is most efficient. Right? In fact, that's what nature does. Once they figure out something work, what they do, they copy, right? The cells, DNAs, right? All our brain. Our brain anatomically is not that different from the rats. Okay? We scale, but the area is much larger, right? So hence, we scale the right thing. We scale the complete system. We scale the highly efficient, most efficient systems. That's what we need to learn from the nature. Thank you.
Thank you very much.
Thank you very much for the inspiring talk. I have a question. In your intelligence model, what is the role of the symbols? To give you more context, you talked about the sparse representations and low-dimensional representations. And what do you think about not naming those dimensions? Can't those help us to do better reasoning? And isn't that how human intelligence also works?
Beautiful, great question. Actually, yes. See, I mean, you can see the whole encoding process is a compression, but also it's a logic coding process. We do have to lose something, but some things we keep what's essential. So the whole process of reduced dimension, but also discretize things. If we see things, patterns that with high probability shows up, we may even assign new names to it. Chinese call it 苹果, British call it apple. Okay? We give it different names. So that's actually how the symbols through this discretization, through this symbolization shows up. Language appear to actually code things with high probability, with high frequency, right? So that's actually happened. Now, there's something interesting, different though, but that's still empirical. But the mathematical language is very different, right? Now, mathematical languages, we still don't know what happened. For example, we know counting, right? For example, using counting. Even dogs, dolphins, if you train them, they can count up to 20. I saw some facts about it. So human, we can count. But suddenly, at some point, we know the notion of natural numbers. We can count to infinity, right? And then early Euclidean space, continuum, time, right, allow us to develop very abstract notion. Honestly, we don't know what is the mechanism behind it. Some people may say maybe it's extension or varying form of compression. Abstraction is extreme form, but what is happening is there isn't different from the compression we talk about today. I'm not so sure, right? So there's a difference between knowing logic or discovering logic, knowing a theory, discovering or producing a theory, right? So the science, mathematics actually allow us to learn knowledge, acquire knowledge in a very different form. We are proactive now. We formulate a hypothesis, then test it. We never do that in the past, right? We sort of observe, we try to predict, learn from our errors. But the science allows us to in very organized knowledge inquiry. It's a very, very different form, optimization form. But nevertheless, right, overall, it's trying to encode useful information of the world, right? So that's still something I don't think any of the modern, AI system has that. We're playing with the symbols, but we don't quite understand the meanings. Yeah.
Okay, great. I think we have time for one last question, but you will be here afterwards. Yeah. Please.
Okay, Professor Ma, thank you for your talk about today. I'm very interested in the topic you mentioned about closed loop and active inference. So I have a question about, I observed from the nature, that for human, from person to nation, all these layers, they have some kind of competition in terms of game theory. So I'm wondering, does game theory exist in your framework? And if intelligence is fundamentally related to game theory, what games they are playing?
Actually, this actually follow related to the lady's question. Beautiful question. In fact, I'm really glad you asked it. So in fact, from our study, we found even to close the loop, to be able to allow our brain to learn things internally, to make sure the distribution match with the data distribution, right? You need to play a game. You need to be proactive, right? So hence, even just to learn empirical distribution, learn that correctly, is the game type mechanism is actually necessary, not, right? Hence, so then you can say, maybe it's because this mechanism allow us to become proactive, to check if our memory is right or wrong, right? Now maybe allow us to discover even causality, allow us to be a little bit proactive, right? So hence, even learn data distribution, if you want to learn this self-consistently, not end-to-end, okay? You need to be self-critical. Self has that mechanism built in. That probably extrapolates to allow us to discover abstract notion, to hypothesize things, and to theorize things, then to verify it's correct or not. Okay? I believe there's a strong connection there. Because, I had some exchange with Julia Pearl, right? Earlier, I was talking about the learning data distribution, saying that you need a game-like mechanism. But causality is that is by definition is anything you cannot learn from distribution, you cannot learn from correlation. You have to have counterfactual experiment, right? To hypothesis testing. So then I was replying to him, well, turns out even learning distribution correctly, especially learn that in a self-consistent way, you need to have a game mechanism built in. So maybe that mechanism move on, start to evolve into something, we can actually be more proactive, right? Figure out what's new out there. Not just what I currently observe. Maybe I can imagine, maybe hallucination is not such a bad idea anyway. But scientific hallucination, not a random, not a 胡思乱想, okay? But guided, educated guesses becomes very useful.